My name is Andrei Kostin, and I'm very happy and delighted to be here at Black Hat Asia in Singapore. Today I'll be talking about automated dynamic firmware analysis at scale. And as a particular application to this, we'll show a case study on embedded web interfaces. Very short, who am I? I'm fresh PhD, and I'm interested in embedded security in general. And I run the firmware.re project, which is an ongoing process, and it has a lot of things to be improved in the future if you try to use it. But about that later. So with IoT IoT hype, we know that embedded devices are everywhere, right? They're like in our health, in our homes, in our offices. Everything which is used to be called embedded now is called IoT, but at the end of the day, it doesn't really matter. What we noticed lately is that the embedded devices, they're not just simple and dumb as they used to be or disconnected, but they're getting smarter and more complex because they have to support different kinds of protocols and APIs just to address the needs of the IoT, right? And the development needs and the rich application needs. So they include various kinds of APIs and protocols like XMLs and JSONs. Moreover, compared to a while ago, most of these embedded devices, they are getting interconnected more and more. What means that most of these embedded devices, regardless whether they are new or old, they are put online via the composition, especially for the old devices, for the old embedded devices, where old unsecured devices are put by composition via various interfaces, RS-232 to Ethernet, to the internet. And most of these devices are put online for various reasons, for providing functionality, but one of the main reasons to be put online is to provide some kind of a remote management or some kind of web interface, right? Most of these devices are being administered via the web. Even though some devices support still FIC clients or telnet kind of protocols, the web is the de facto standard to managing this kind of devices nowadays. In comparison also to the smartphones and the cloud application, but at the end of the day, they use some kind of a REST API, some kind of web-based technology. So that's why we focus in this work on embedded web interfaces. The idea is that we know that in our previous study in Usenix Security 2014, what we did, we went on the internet and downloaded hundreds of thousands of firmware images. So we know that there are hundreds of thousands of various versions and various devices and various vendors' firmwares. And it's a lot of data to process, to analyze, and those are hundreds of thousands of firmwares, right? We also know by various reports, especially by Cisco and Gartner, that there will be like tens of billions of devices connected to the internet by 2020. The number varies from 20 billion to 50 billion, but in general it doesn't change the problem essentially. I mean, whether it's 20 billion or 50 billion, it's still billions of devices being online, running various types of firmwares. So you see that both of these problems where firmware devices and firmware images and embedded devices, they come in large numbers and can be in large combinations, and all of them are online, and many of them expose web interfaces. So with these two observations, we don't call these facts because it is really hard to estimate the number of real firmwares in the world or in the devices, and also it's really hard to estimate real number of connected or embedded devices in general. But with this kind of observation, we get a set of challenges, namely that there is a large number of devices and there is a large number of firmware files. We also know that these are highly heterogeneous systems, and what does this mean is that many of these devices are not your usual x86 or 32 or 64 bits kind of processors, but they come in different forms and shapes and different CPUs and microcontroller units. So they run completely different kinds of software than what we used to analyze massively for malware or non-malware for x86. Also, they are getting increasingly smart and connected, so they add additional services and protocols inside them, but they're not all the time like the usual suspects. And there's also all these firmware images as opposed to, let's say, streamlined Windows update or macOS update or Ubuntu update. All this data is highly unstructured. You rarely will see an embedded device which has these streamlined update procedures. Usually you'll have to do and download some kind of very obscure file in a zip and then try to drag and drop it in a firmware into a web interface, or use some kind of a bus pirate device to put this file through RS or UART interface. So this data is also highly unstructured. And at the end of the day, we will also notice that these vulnerable devices are being exposed every day on the internet thanks to Shodan and Census and Zoom-I kind of projects, right? Where you can go to a search engine and just put the query for a particular set of devices and you'll find all these vulnerable devices. So these challenges prompt for some solutions which we try somehow to address in our previous and our current research initiatives. So the large number of devices, for example, challenge prompts that the solution we come up is analysis without devices. First is because we don't have unlimited budget to buy all the devices, and even if we could buy all these devices, that will be a logistic nightmare to get all of them, to put in a physical space, to connect them, disconnect, configure, and so on. So this is a logistic challenge. The large number of firmware files, of course, we need fast and scalable architectures to analyze this. We cannot just use a very sequential, very old style method. We need to scale to the number of files. So we have hundreds of thousands of firmwares. We need an approach which scales, and we can just throw as much resources as we can. For example, in private clouds, use VMware kind of solutions, or using Amazon Web Services, so it can scale. The highly heterogeneity challenge prompts us to develop generic techniques. We cannot develop techniques for ARM, and then once we get in firmware or an embedded device for MIPS, we need to redevelop it from the scratch, because it will be like a loss of time and resources, and the techniques must be generic, right? So we write it once and run every time, regardless, or ideally regardless of the architecture and software behind the test. Also, we know that interconnection and the smart thing expose APIs and web interfaces. So these are the first things which get exposed on the internet when you connect your printer, your CCTV camera. Most of them have dished CPs, dynamic DDNS. They end up on the internet if you have public IP address spaces, and people find them on Shodan and so on. So these are the things which we want to focus first in order to find the vulnerabilities and secure them first, and then focus on the kernel and the other stuff which is more like local kind of exploits. Also, the highly unstructured data prompts for machine learning algorithms. We'll not address this in this presentation, but you can look it up in our related papers. And it prompts for machine learning for large-scale data. And vulnerable devices exposed on the internet prompts for a solution which is technology independent to fingerprint the device. For example, when you see a device in Shodan, or when you see a device online, an IP, how confident are you it's not a honeypot? How confident are you it's a particular firmware version? How confident are you if you're a system administrator and you see, let's say, a particular router in your network, how confident are you is that it's a particular firmware version which is vulnerable to a particular CVE or not? So we need fingerprinting techniques which can fingerprint these billions of devices easily and to be technology independent. One way to do this is to use the web interfaces for the web-enabled devices and use other kinds of techniques for non-web enabled devices. So how we do the one approach to do dynamic firmware analysis is basically to take the device, each device, connect it to your network, connect some kind of JTAG or a UART debug interface, and start poking with the device and see what happens. But as told previously, we don't want to mess with devices, so we try to do analysis without devices. And what it means, we collected the large number of firmwares which we unpacked, so it ended up us with a lot of unpacked firmwares, right? And those unpacked firmwares, many of them are partial firmwares, meaning that they just upgrade particular set of files. They don't ship the entire firmware image, and they don't ship the entire operating system and the entire web interface. They just patch a particular or upgrade particular features. Luckily, some of these firmwares, they come as a more or less full kind of firmware images. So we take these unpacked files from our Usenix security study. We perform this firmware selection, meaning that we try to detect the full file system or full upgrade firmware images, and we perform some additional selection, which I'll explain now. The idea is that we focus, as a proof of concept, we focus on Linux-based firmwares because they are the most easy or the easier to tackle in the first place compared to other non-conventional or real-time operating systems like FreeRTOS or VxWorks, for which there is not so many tools available. For Linux-based systems, we have tools and we have understanding how it works, and it's just a matter of different CPU architectures. But in general, everybody knows Linux very well. So that's why we focus on Linux file system, Linux firmwares, and that's why we perform this firmware selection where we select full firmware images and Linux-based, which are also Linux-based firmwares. In addition to that, because we focus, for example, on web interfaces, we also filter only the firmwares which have a web server or web server related files. For example, if there is a HTTPD or light HTTPD or BOA kind of a web server, or there are various HTML, JavaScript, PHP, Perl files in a web document root, we select only those files. And this is a particular case because we focused on the web interfaces as mentioned, but in your case, if you want to do the same kind of an approach, you would like to focus on firmwares which have, for example, UPnP related files. UPnP is known to have CVEs and known to have vulnerabilities. So you might want to filter out or select only the firmwares which are full firmwares or not full firmwares, which also has UPnP configuration and binaries inside. And this is more or less easy to detect with various static scripts like strings and other techniques, right? Once we select these, we do file system preparation, and why we mention this as a step, as a heads up, is because when you unpack a firmware, usually the unpacking of a firmware, if you look at our Usenix security paper, is not 100% reversible from the vendor, because sometimes the vendor uses customized packers or customized formats for file system like SquashFS or JFFS2. They use various kinds of configuration bits or kind of obfuscation bits. So when you unpack a firmware, using binwalk or your favorite other tool, then the firmware gets unpacked not as exactly as the vendor intended to be on the device. So sometimes you get broken SIM links, sometimes you get messed up files, and you have to fix this, right? Sometimes the firmwares come as multiple file systems in the same image, so you have to basically take all the file systems, which one is MTD block, the other is QuashFS, and you have to glue them together as if it was a complete file system once the device is booted. So there are various artifacts which you need to account, and that's why we call it file system preparation, where you kind of fix the file system so it looks like a complete Linux image. Then what we do is we take these fixed and filtered out firmware file systems, the complete ones which have a web server, or in your case might be different network service, and we throw them into a scalable cloud. And again, why I mentioned scalable, because you want, if you have tens of thousands of firmwares and you want results by tomorrow, you just plug in 10,000, you clone 10,000 nodes on Amazon Web Service or in your own private servers, and then you have 10,000 virtual machines doing your job for tomorrow morning, and you have the results. And what we do in these nodes, in these processing nodes with the firmware, we do two things. The main thing is the dynamic analysis, and the additional thing is the static analysis. And I'll explain a little bit later why we do it as an additional thing. And then the dynamic analysis implies that, okay, what is dynamic analysis? The dynamic analysis is the process of finding bugs or vulnerabilities for the security domain while actively executing the executable or the binary or the system under test. The static analysis is trying to find the vulnerabilities or bugs by not executing the system or the binary, and just by looking at various properties or various features of the system or the files, right? And this can be source level static file analysis, where, for example, if you have PHP or Perl or Python, you'd have the source code most of the time, and you'd throw it into a static analysis tool for PHP, for example. And in our case, we use RIPS tools, RIPS. There are also various static binary analysis tools which take binaries like ELFs or just simple binaries, chunks of code, and they perform different kinds of static analysis, trying to find buffer overflows or infinite loops and denial of service just by looking at the structure of the binary code. Unfortunately, there are not so many static binary analysis tools, and in particular, there are not so many static binary analysis tools for embedded systems like ARM, MIPS, PowerPC, and so on, even though there are some scripts, but there are not so many tools or so much knowledge in this. That's why we focus mainly on the static source analysis of PHP files, and in our case, we found that around 8 or 10% of the firmwares actually have PHP files, and this is not surprising because PHP is a little bit heavy for embedded devices, and it's usually, they don't usually use this kind of interpreted languages. They use Perl, or they use just simple HTML, or just use some hard-coded custom binary web server, which has its own in-house interpreted kind of escape tags, right? Now, after we do the dynamic analysis, we of course collect the results and try to see what kind of results we get from the static analysis tools and dynamic analysis tools. And usually it involves more or less engineering effort, like taking the XML out of the tool and looking for the particular type of vulnerabilities like XSS or buffer overflow or command injection, and then trying to just put this in a database or in a report so it can be easily recovered or filtered and so on. And then we feed it back into the file system preparation or other phases of the process, Why is that? Because, for example, in the results we can have that the emulation or the dynamic analysis failed, and we see in the logs that there was a symbolic link missing or etc password is missing, so we feed it back into file system preparation and so on. So this is an iterative process because, again, as I said, you never know in advance how badly is your firmware being unpacked, unless you have very good heuristics in the first place, but even so, with very good heuristics in the first place, it's still hard to know, right? But the question is, okay, dynamic analysis sounds cool, but how you actually do it? I mean, if you don't want to use devices and, okay, how you do it, a dynamic analysis on a complete file system, on a complete embedded firmware. And the usual answer you'll find on the internet, and most of the experts will tell you that use QEMU. And this is what we do. It's keep it simple. We try to use QEMU, and for those, I'm pretty sure everybody knows, but for those who don't know, QEMU is a quick emulator, and is a free and open source emulator, which basically supports like a dozen or more of architectures. It can run standalone binaries or system-level binaries where you give it a kernel for ARM, MIPS, PowerPC, and the file system, and it will execute as a normal system with all the inputs and outputs. But the thing is that, okay, we have plenty of choice of emulating the firmware. Which one is, or which ones are available in general, and how to choose which one suits our needs. So we had like a decision to make which kind of emulator to use, and we had to make just to know exactly where we stand on at present, and we made this kind of a simplistic chart where there is the ideal emulator, which is which is a perfect emulation for any architecture, regardless of the binary and firmware you give it. It will emulate you perfectly, and you will not have to bother with anything. You just supply it any kind of file, it will figure it out on its own what to do, and it will provide you an emulation of that particular system. Another approach is to use the generic system emulator, where you supply to the emulator, whether it's QEMU or any other emulator, you supply the original firmware and the original kernel of the device, right? Because the device, as we mentioned, is a Linux-based. There are kernel devices compiled for this particular, for those particular embedded devices, because they have different kind of peripherals like flash memories, specific ports, Wi-Fi and Ethernet chipset, and so on, or system on a chip kind of things. The other approach is to use the original firmware and then use a generic kernel where you can compile your own kernel with all possible modules and all the debugging options and instrumentation options and logging options. So basically, it will be a big one, it will be a big kernel, but you try to compile everything in one kernel and supply it to the emulator, and hopefully it will load the firmware as if it was a natural or original kernel of the device. Then there's also the possibility of userland emulation, or what is called the architectural chroot, where you take the original firmware, but you don't execute it basically in an emulator per se, but you use the userland emulation. For example, you can run the ARM or MIPS binaries. You can run them on x86, for example, by using a feature of a Linux kernel and supplying QEMU / -user - ARM or QEMU - user - MIPS as an intermediate translator of the CPU architectures. So basically, you can execute the firmware without actually needing ARM or MIPS kernel. It will execute inside the x86 kernel and will use the userland translation. And finally, for particular cases, you can actually avoid at all the emulator by using the hosted approach, where you basically take the application, or in our case, it's web document root, and put it in a normal x86 server in your var www Apache Lite HTTPD folder, and you will hope that this document root will load up and will execute some parts of it. Of course, with all of these choices, there are drawbacks. And for example, we cannot use the ideal emulator because it doesn't exist, at least not in open as we speak, or not knowingly to us. And potentially it doesn't exist yet because it's really hard just to take a random binary for random architecture and emulate it perfectly on the fly. So it's kind of a unicorn, and we really want this to exist, but it's hard. We cannot actually use so much the original firmware and original kernel, and the reason for that is that less than 10% of the firmware we analyzed in previous works and in current works is that less than 10% of the firmware come with actual kernel. And if you look at the embedded devices, most of the embedded devices, they run on kernel 2.6.32 or 2.4 or 2.2. And the thing is that they just compile once the drivers, the kernel, and what the firmware updates usually contain after that is just the application, the user land, maybe the libc, maybe the utilities or the web servers. So in fact, you don't have so many original kernels in the firmwares. And of course, you can get them by going on the device itself and dumping the memory or the flash dump and the RAM and so on. But the problem is then you need to apply manual techniques, because dumping a chip, you need to connect some wires and do some tricky things, and it doesn't scale, and we want to scale. You cannot hire 10,000 electronics engineers just to solder wire in a fleet of billion of devices. So it's a really a no-go unless the vendors provide the kernel themselves, which they usually do not. Unless they're caught red-handed with Linux kernel and they have to make GPL open source, and even then it's not easy to compile exactly to the kernel of the device. Then the user land emulation, as mentioned, is the architectural chroot. Doesn't work very stably, and it doesn't perform, as mentioned, it doesn't perform system level emulation. It performs mostly like a binary. If you have let's say a binary, like a test binary, you can execute it on a x86 computer without a kernel, but it's only the binary. And many times the firmware or the embedded devices, a particular binary depends on existence of many other binaries loaded in the memory, or existence of various device drivers, which you might not have on your x86 test system. So if it's a very simplistic binary which just connects to the network, yes, it could work. But sometimes, or many times, the embedded device tries to access the /dev/nvram or /dev/ some other kind of special device, and you don't have this in a x86 test system unless you emulate it via other means, and it brings you back to the full system emulation. So for our test, we chose the hosted web application testing, where for the document roots we detect, we put them on a x86 Linux in var www and test. And for the main testing, we use the original firmware and the stock ARM MIPS PowerPC kernel, which is precompiled, and we use it as it is. So there are some errors about emulation accuracy, the complexity, the speed. So going in either of this direction will give you more or less speed or more or less complexity or emulation accuracy. And however, these directions are not linear. Sometimes it will vary greatly. For some of them, the increase or decrease is not quite linear. For example, the complexity for ideal emulator is obviously exponentially. It's really hard to get it, to implement it and get it working flawlessly. Okay, so just a very quick overview how we do this. So we have because we want to be scalable, we have a, let's say, Ubuntu 14 or whatever your preferred distribution is. Virtual machine is a virtual machine because, as we mentioned, we can throw it into VMware, private server, we can throw it into Amazon Web Services, we can throw in any other web cloud providers, and it will scale. We just take the IPs, we do distributed Python over SSH and so on. And you can see that this virtual machine will run a Linux kernel, but it doesn't affect us because inside every Ubuntu machine, in our case, in our particular case, we use QEMU with its own Debian squeeze RML or MIPS or PowerPC kernel. And basically, and also there's all the tools from Debian squeeze distribution like vget, curl, netstat. So it helps us to basically instrument the environment where the firmware will be executed or is executed. And what we do next is as we mentioned, after we do the file system filtration or selection and preparation, we put it inside QEMU. And that's why we called it firmware user space versus the Debian user space. And then what we do, we use the chroot. And again, I'm pretty sure everybody knows, but for those who do not, chroot is basically a method or a way to change the root partition in a particular environment so that you can take a particular file system and say that for this particular session, these files, it can be in TMP or wherever you put them, will be the root file system where you'll find /dev, /proc, /etc, /everything. So basically it's a technique to temporarily change the root partition of a given system. And we take advantage of this chroot, so because it's, in our case, it's a Debian ARM, and for Debian ARM, we load firmwares for ARM architectures. For Debian MIPS, we load firmware for MIPS architectures, and then we do chroot to the firmware. And there is a bin sh or bin bash or bin busybox, which provide the shell, and this chroot will basically load the firmware file system, right? And will pop the prompt of the firmware. And then we just invoke the init RC script because, again, we mentioned we focused on Linux-based embedded firmwares, but similar approach can be used for other kinds of systems where you don't invoke init, but you jump at a particular address or execute a particular executable to initialize the system, right? And the init will run the RC scripts and will start other services. And what we are interested in our case is that the RC scripts will start the web server with all its document root components. And interestingly enough is that some web servers will have native CGIs, like these are kind of the binaries for ARM or MIPS or PowerPC, which execute something on the device or in the emulator and return an HTML response, something. And sometimes these native CGIs or Perl and PHP will use some local utilities like ping or some shell to copy a file. So these are potential ways to, for example, to do command injection and do other nasty stuff on the device. And this is what we try to look at very quickly, automated and in very fast manner. And sometimes they also have file read and writes interaction with the file system. And this is also where we're interested that the attackers could get etc password or any other sensitive details or configuration files. So in our case, if the RC scripts do not start the web server, sometimes the RC scripts do not because they don't find the NVRAM, and because they don't find NVRAM, they don't load the configuration, and then they just stop. We sometimes force the web server. We detect all these web servers like BOA, Light HTTPD, and so on, and we start them by forcefully executing them. Sometimes we get lucky and they execute. Sometimes we get unlucky and they don't execute, but it's not a problem. It's a scalable. We don't want to find all the bugs. We want to find the bugs and vulnerabilities which are easy to find, fast to find, and easy to patch, right? And then what we do is we fire our fleet of tools. I mean, you can plug here any kind of tool. We plug Nessus, Metasploit, Nmap. For web vulnerabilities, we use Arachne Scanner, which is a very cool, very efficient open source vulnerability scanner for web applications. And optionally, we'll also use OWASP ZAttack proxy and W3AF, but they're a little bit, in our case, they were less efficient than Arachne. In our case, Arachne worked very well, but we also use the TCP dump to record all the back and forth with the web server. Why is that? Is that because basically these tools perform fuzzing, and sometimes a crash or a command injection and so on is not a result of the last input, but is a sequence of inputs. And you want to keep these TCP dumps between the tools and the web server or your emulator so that you can recover the inputs and reproduce the crash or command execution later. And for these reasons, Arachne have this kind of random session identifier, so you can track back the particular testing session and so on. So it's very useful. So very quickly about the data sets. So we started quickly with almost 2,000 firmware files, and we filtered out around 1,500, which are Linux-based full file systems and show potential for web server inside. And this is the number of vendors at each stage. So basically, we started with 54 vendors and 2,000 firmwares, and then we filtered out and we are left out with 49 vendors and 1,500 firmwares. And as I mentioned, sometimes we need to fix or prepare the file system, and that's why we get from 1,500 back to almost 2,000 file systems. So basically we have 1,500 different firmware images, but we end up with back around 2,000 file systems because there are multiple ways or there are multiple versions of etc. There's etc, etc read-only or etc factory default. Sometimes there are web document root for different languages, for example, www_English, www_French, www_something. This is the way they do, and there's different symbolic links. So we end up with kind of different kind of file system, right? And then we throw them in this processing cloud. We figure out that around 500 do chroot okay. The rest fail to do chroot, and sometimes it's obvious why they do not do chroot, because if you look at a binary file, for example, for BusyBox or shells and so on, you'll see that they look like MIPS or ARM, but there's a lot of variety for MIPS and ARM as well. I mean, there's MIPS big endian and low endian, but a little endian, but then for ARM, there are different kind of EIBI, like application binary interface, where you have ARML and ARM-HF. So you cannot run an ARM-L file on ARM-HF and so on. So sometimes it's just, they do not run, right? Sorry. And then after we do the chroot, we start to the init scripts and RC scripts and so on. We try to run the web servers, and almost half of them open the port 80 or port 80 and port 443. Some of them open also HTTPS port. If you look in the paper, you'll see the details how many of these firmware files contain HTTPS certificates and how many of them open HTTPS ports, but it's less than 25%. So less than 25% actually intend to open an HTTPS port for embedded devices. And even in those cases, the certificates are self-signed, they are not regenerated, they are static, so basically you can do man in the middle. And there's no very little little amount of cases where the user can upload a proper certificate authority and a proper CA bundle to the device so that the device is really like trusted by a real CA authority, right? And then what we do, as mentioned, the static and dynamic analysis. We do dynamic analysis on all firmwares which started the web interface, and we do static analysis only on the firmwares which had PHP. And we end up with 13 vendors and around 185 firmwares which had high-impact vulnerabilities. And by high-impact vulnerabilities, we mean the XSS and command injection in the web. And why we also mention XSS as a high-impact vulnerability is because there are papers which show that you can do a stealth firmware upgrade by just using XSS and CSRF. You don't need particularly command injection in some cases. So it's a really high impact. So, or sometimes important router credentials can be stolen by using XSS, right? So we also do some, because you saw there's almost 70% chroot failures. We cannot chroot, and there's 50% web server failure. And understanding the failure basically helps you understand where your system is constrained and what you can do to improve the system. And what we did is we did failure analysis. We took from all these failure logs, we took a random sampling, and we selected a number of logs which correspond to 95% accuracy and 10% confidence interval. So what we saw after analyzing these around 100 something logs is that if we apply relatively easy fixes, 70% of the chroot failures can be avoided. So basically, sometimes the chroot failure takes chroot takes longer time or is not properly detected because the environment is set up in a strange way. So if you improve the chroot mechanism and chroot detection, then you can improve the chroot process itself. Then for the web servers, only 35% are relatively easy to fix. The rest are either binary CGIs, which depend on some non-existing tools, or there are various other reasons which are not very easy to fix, and you have to actually manually dig through the log and fix those, which doesn't scale again. In general, we also try to look at how many architectures are for ARM and MIPS, and we see that ARM and MIPS are somehow close, 35% to 36%, and they share almost equally the chroot success and web server success rates. So they're kind of head-to-head. There are not extremely many differences, but we also see some other unusual architectures. For some of them, there is no QEMU support, or you need to use a vendor-specific emulator or simulator. For some of them, there is at all no emulation support, and you have to write your own in QEMU, which is, again, an engineering effort, but is a considerable one sometimes. But we look forward to checking those as well. The idea is that if those are Linux-based systems and you just can build a QEMU which supports this architecture, it's easy to plug in this kind of a system just by adding the QEMU binary, and it will support any other architecture. Then we also analyze the web servers, and there's mini HTTPD and light HTTPD which are leading the way, and there's not so many BOA and THTTPD. You'll see a lot of these web servers which just contain HTTPD with various prefixes and suffixes, and you just get lost, and many of them are called HTTPD, and they're in fact not Apache web server as you would expect. They're basically some customized binary which run in a single binary, the port 80, the port 443 threads, and they do everything inside. You don't even have a sitemap, you don't have HTMLs. They serve everything from within the binary. So sometimes you will, that's why we put empty or unknown banners to 26%. Sometimes it's really not conclusive to understand what the web server is. And that's the reality. Sometimes of them just ship a blob and that's the web server. We also, from those almost 500 emulated, successfully siege root and emulated firmwares, we try to see what other services they start. And there were 207 instances, which you can see the distribution. Many of them started, like 91 and 84 started the port 554 and 555. And this is because many of these firmware in our dataset are basically CCTV cameras or DVR players. And all of these systems, they usually open these ports to stream the video feed on these RTSP protocols, right? So what it means that, well, from security standpoint of view, we don't know what it means, but it shows that there's a lot of devices which actually stream, and if you have been following the news, there's the images.shodan.io, which basically shows all the CCTV cameras they can find online. And this is actually how they do. They look at these 554 and 555 ports, and if you look at our results, it makes sense that there's a lot of devices or CCTV cameras which are plugged online so that the owner can check his home or his office from remote, and they're just plugged online and you will find these ports openly. There were also other ports like Telnet and DNS and SSH and various debug ports which were low number and need more like hands-on analysis, but just throwing a fuzzing at them, which we consider is a very good way to see what other bugs are there. So finally, we can see that by using static analysis on the PHP files, we had 145 firmwares which had PHP files, and basically the tool reported us almost 10,000 various results. I mean, various notices in different modules, 5,000 cross-site scripting, and almost 1,000 command injection or execution. Some of these can be false positives because the static analysis tools, as you know, they are just static analysis tools and they have their own limitation. They just try to give you a hint, but it's not 100%. You need to verify, which is a challenge we identified in 2014. But sometimes it's not just looking at a particular library version saying, yeah, this library is vulnerable. You need to test it to be sure it's vulnerable. The same is here, but the big number of vulnerabilities shows that there is a lot of potential to actually one of those vulnerabilities to be, or one of these reports to actually be a real vulnerability. And in fact, if we run the dynamic analysis and we see that we find 45 firmwares automatically without any customization and so on, we find 225 different issues like CSRF, cross-site scripting, and command injection or execution, and I'll show you in a short moment some demos. You'll see that, yeah, they can be found. There's a lot of other low priority reports like backup files or no X-frame options and so on, but this is not surprised because the web servers are outdated or are custom-based and they don't follow the latest security practices, so they don't include all these headers, HTTP headers. So one example is, for example, this kind of large-scale quick analysis helps us to actually not just detect new vulnerabilities or 0 days, which we'll show some in a while, but is also helpful to understand if some vulnerabilities are exist, but they're not completely described, right? For example, there is a vulnerability from 2011, and this is the name, and it basically, if you read it, it says that only these devices are vulnerable. WNAP 210. By visiting Recreate PHP, you get pre-authentication, admin privilege escalation. And the idea is that automatically we found or validated this vulnerability on other devices on 3 different versions for other devices. So I have the virtual machine here, and hopefully everything is running. So this is the IP of the virtual machine. There is no trick in it. As I said, we start the QEMU, and QEMU have this nice feature that it can redirect particular port numbers from QEMU to the host file system. So for each emulator we start inside, we can assign different ports. So for the first firmware is well, we start 3 firmwares, right? I'll give you an example what they are. This is the first firmware, which has this SHA-256, and this is the actual firmware where it comes from. And you can see this is a Netgear WG103. It's obsolete. There's no more firmware upgrades to it, so it's not very nice. But we emulate all these firmwares. So version 2037 will be on port 2080, 222 will be on 3080, and 2025 will be on port 4080. So let's go to 2080. We'll just use some bogus. It doesn't work, right? But if we do recreate, it says recreate OK, and this is the first sign that the recovery of the admin session is successful. And if we go back, you see that we are logged in. Okay, and this is running in the emulator. I don't have any devices, and it's not some remote tunnel to some. Okay, and well, we can see that these are. You can see that, of course, there's no wireless radio because we didn't load the wireless kernel module for the device in the emulator and so on. But I mean, this kind of errors occur. As I said, failure analysis helps you see this. But we can look at the logs, and you see that's started now March 31, and it's excuse me. You'll see that this is BusyBox particular version. Compiled in 2011, and you can see also the time zone, so you can basically know which is the development center which did it, right? You know exactly. Sometimes you see Korean time for some Korean products and so on. So you basically know who is the guy or the development center or server which produced this particular thing. You'll see some errors and so on. But the idea is that you see that it was easy to get as admin. Then we can do the same for the other version. Here we are not logged in. If we do the same thing, we are logged in, and in the logs, you'll see a different log because it's a different firmware, so it behaves differently, and you can also see that the timestamp of the BusyBox is different, so you can all see the different versions come with different binaries, but you can still identify them based on different fingerprints, strings, or log files. And just for the pictures to be complete, I'll just do this for the last thing. And you can see that it works flawlessly on all these 3 latest firmwares from. And I said this is obsolete product. It doesn't receive any firmware upgrade. So if you see this kind of a device in a network, you have 100% hit that you're getting admin, and then you're getting command injection because it also has command injection with no updates, right? And this is actually the command injection I'll show you is a 0-day. This one is a not 0-day, is 5 years old vulnerability, but it's still there, right? Because they didn't even bother to check on all their firmwares, they who produce the firmware. I mean, and it's easy because you can just spawn many emulators. Yeah, so this was the first thing. And you see this is even older one. This is 2010, not even 2011, and so on. Okay, so let's see some other quick things. So we also redirect the 20. I mean, you can do whatever you want. I mean, I'm showing how we do this, but we also redirect the port 22 of the emulator, so we can log in into the firmware, into the QEMU container, right? And let's say in our case, we'll just try to so we are logging in now in the QEMU container, and should work. Oh, yes. And we used the Debian precompiled images, and they come with. You can find all the details in the paper where we get them. But you see, in our case, it's a Debian MIPS based on 4KC Malta development board, but it can be different. So just to show you, the chroot command is working something like this. And basically now I'm root. You see that it's the busy box, exactly the one which you saw in the web interface. And you can basically run it as a normal firmware, but we run it automatically. I mean, this I'm giving you just a sense of how we do it, but all these are scripted. Everything is sent as an automation script. And now what I want to show is being in the virtual machine of which runs the QEMU, because I mentioned that we are in this virtual machine. I can show you very quickly. Sorry about that. Because all these web application tools, they can crawl the web interface. If it contains hundreds of files, it will crawl all these hundreds of files and then execute all known fuzzing, XSS, command injection, and it can take hours just to perform, or well, depends on how big is the web application and how fast the emulator is. It can take hours still to get everything. So just for the sake of short demo, I show you the 0 day, which is in these files and is documented in our paper in the links. Basically, what I am doing is that I'm mentioning to the Arachne web scanner to scan just these URLs in the thing. It found automatically, but again, right? I'm showing you for the sake of shortness. It's there. I already created it, and if I run the, you see that I'm running the, let's say, Arachne. I'm running it on localhost. It's localhost because it's virtual machine, so the QEMU is inside virtual machine, so it's a localhost, and it's the same port 2080, which I showed you earlier, right? Is the 2080. It's still there. Is fine. It's timeout, but I can recreate again the admin session, right? And basically, what I'm asking is that I'm asking to perform XSS tests on the sitemap, on the limited sitemap, which I showed you earlier on these files. And you can see that there's something we, okay, I know what it is. Okay, so you see that there is already one cross-site scripting detected in this particular file, in board data 102 PHP, and it says it's MAC address. So you see it found basically in a matter of seconds, right? I mean, and if I just prepared already the thing. it's add the MAC address field, right? And I'm just having the ready exploit. And you can see that some of these files are not even session protected, right? I mean, you need to log into the web interface, but some of these files are not protected. And if I do like that, I'm getting XSS. And then what else I can do is I can do, for example, what we actually do, again, automatically, we specify to the thing. So, no. I'm logging again in QEMU to show that there is no command injection indication file, and then I'll run the Arachne, and you'll see that it basically will detect again in a matter of seconds. And so what we usually do is we create, in your case it can be different, but we create a file which is command injection something, and the random number, you see there is nothing like here. And then what I'll do, I'll just run again Arachne on the same 2080. Okay, I'll again limit the sitemap, but it can go through all the sitemap, through all the PHP files, on all the CGI files, and I ask it to check for OS command injection or to test. And the thing will just run. Oh. Come on. Just 1 second. Okay, so basically it started doing the OS command injection. Sometimes you see that the tools are also getting stalled, so you have to kill it, but if you do it automatically, you don't care, right? And you see that we have some files created in dub and in temp as command injection firmware. So basically what this tool does, you can put in OS command injection module to touch a particular file and so on. And for this particular example, let's go to TMP. There is this command injection. There is no password file. I already prepared the exploit. I mean, it's easy to create once you get the report from the Arachne, and we'll run it. And then you see that update success, but we don't care. And then you'll see that there's etc password here from the device, just because the Arachne tool managed to show us where exactly is the vulnerability and so on. So this is just one example what happens like in automated manner and so on. I think I need to wrap up a little bit late. The slides which will be available, you have all these details of vulnerabilities. There's another, and it affects a great deal of devices like listed here. All of these devices are affected to this XSS and command injection. Some of them have very bad fixes, like the vulnerability still exists. And there's another vulnerability in some Netgear. These are basically responsible disclosure 0 days, because we notify the vendor it's more than 90 days and they didn't respond or fix. So we are disclosing these. These are very expensive devices, wireless controllers, and they also have command injection in them. We detect this by using the hosted application method. If you remember, we had the emulated and the hosted. And using the hosted thing, I can show you that we have put inside the, let's say, this path. This is our, we are now on Ubuntu, right, x86. And if we check the var dub and the document root from this firmware, we have this bunch of files, PHPs, and then if we execute the particularly crafted exploit, which is in logging handler, and we do cat etc password, then we'll get the password back. And some other data from the script, which is some JSON file for APIs. So yeah, you can see that both methods, they work, like they work the QEMU, the emulated, and all this is automated. I mean, it's nothing fancy about automating this. So just to conclude the summary of the results, we found command injection like high impact vulnerabilities, the command injection XSS, CSRF, by using the automated and scalable framework, which applies both static and dynamic analysis and emulated and hosted approaches. And we find these vulnerabilities in around 225. We found 225 different vulnerabilities like that in around 185 firmwares from 13 vendors. Is not that much if you look from the original data set, but by increasing the success rate of chroot and web servers, and by using other techniques, these percentages can go a little bit up. And also, we are not interested in finding all vulnerabilities. We want to find quickly the easiest ones, right? And you can have some references in our papers, which this work is based on our ACM Asia CCS 2006 papers and our Usenix Security 2014 papers. If you're interested in this, should give it a try. And a list of tools for you to try out, which basically we used in our research, and some online tools to find the devices online or to check your theories about various devices. And the three main takeaways which we want to emphasize that the large-scale firmware analysis, as you can see, is necessary because there's a lot of vulnerabilities and is necessary, especially with IoT hype, is really necessary to analyze the firmwares, not just the x86 and the malware and so on. We also demonstrate that the scalable and dynamic analysis of firmware is feasible, and it yields really good results and can yield even better results with some effort, some engineering effort. And we also see, and at least we conclude personally, that many vendors do not perform proper or basic security testing and QA, because you can see that easily, just by running out-of-stock non-commercial tools, very automated environment can find easy serious vulnerabilities, and we don't understand why they don't do this. I would like to acknowledge my colleagues and my professors, and a very important notice that your feedback is very important to me personally and also to Black Hat, I guess. I'm pretty sure about that. And yeah, please rate this talk after you receive the email. Thank you. If you have any questions, I'm sure I'm too much over time, so you can catch me later over coffee, or thank you very much.